Nepal actually it's a western. It is like located in the western coast of Canada. It is close to Colorado. So suddenly we have a university which is started from the business. We have another campuses starting from medicine to engineering. It's an international campus. So I was working there for 3 years there. Recently they have started a campus in 3 years back. I watched it. Yes, so I can easily reach. That's the reason I was. So basically, if you just look at that, I am a micro guy and I am not a nano guy because I mostly work on natural products. Real estate design. I used to also do real estate design. And my PhD area is of biomedical engineering. And I did also the work related to biomechanics application. Now I'm doing interdisciplinary area. I'm just focusing on medical applications. I mean, design for low power applications. Medical applications, like designing low power devices for medical applications. That's my focus right now. So always I start with, because for my class and lectures also I used to do that. Instead of going directly into it, I just wanted to tell some of the history of it. So that's what I start with. So today's presentation I have here is from basic design to machine learning chip design, a comprehensive workflow. We just wanted to start with fundamentals of electronics and let us go through what all the advancements we have through machine learning concepts, AI applications in the real-estate. So that's what my main objective of this presentation. Let me start with, before going into real-estate design, always talk about history of electronics. History of electronics means always we started with way back with vacuum tubes. So there is no vacuum tubes existed now. Okay. So after vacuum tubes, people started using diodes, right? Diodes and P-junction diodes, and after that transistor has come, right? So using P-junction diode, transistor was made. The first generation transistor is what bipolar junction transistor, that is BJT. Then people move to, now we are in FinFET. We use MOSFET, then people move to FinFET, right? So field effect transistors. So the next part, important part of the generations of the IC is we just look at generations of the electronics, we just look at integration and very large scale integration. So what is my small scale integration? Whereas 10 transistors can be integrated into a single chip. Whereas medium scale integration, hundreds of transistors can be integrated into a single chip. Large scale integration is nothing but thousands of such slices in VLSI, because our applications are limited to lakhs of transistors. Because the complexity is also got limited. So very few applications we work on with ULSI and SLSI. So that is a very advanced integrated circuit generation. Okay. So these are the fundamentals you all might have known already. Next, this is the most commonly used. I mean, we always discuss about it in VLSI design when we discuss. What is that? Moore's law. So what Moore's law is? Every 10 years, the integration doubles. But again, practically, if you just look at it, is going beyond that. So this Moore he predicted in 1970, 1950s, so he predicted it, but if you just look at it, is going beyond that. It is going beyond that. Next, we are going to see the numbers. I just wanted to touch up few other things because before going into the topics, because you will not be able to relate it, right? You know, you all might have heard about this, right? Design flow, right? What is a design flow? Basically, if you just look at, there are two parts in the IC design. One is front-end design, the other one is back-end design. So generally, our front-end design starts with, right, we write a HDL program for some particular application. So you have plenty of languages like Verilog, System Verilog, or VHDL, you write a program. There are two main processes in hardware description languages. If you just look at, one is logic simulation, the other one is logic synthesis. So what is the use of logic simulation? Basically, logic simulation is nothing but this functional verification of the circuit or logical verification of the circuit. So most of the programming languages we restrict with simulation only. But when it comes to hardware description languages, we have two main processes. One is simulation, the other one is synthesis. The reason lying here is, so we are working only with digital circuits. We are working only with digital circuits, two discrete values, either 0 or 1. So just by see what you do, actually you write a program for some particular application, you simulate it. So once you simulate it, you get output in terms of the waveforms. So waveform is nothing but it is just the verification of the truth table, isn't it? It's just a verification of the truth table. Truth table, what it says, like you give 1 and 1 as input, you will get 1 as output. Right? Just because I'm getting 1 and 1, for 1 and 1 input, I'm getting 1 as output, I cannot ensure that whether it is an AND gate or OR gate. No, no. For AND gate also, if you give 1 and 1 input, what will be your output? 1. For OR gate also, 1. But whether it is performing actually an AND gate operation or OR gate operation, how you will confirm? So this simulation information is not sufficient to justify the design. So that's a basic problem of digital circuit simulation. So that's the reason people went for a next level of designing is nothing but logic synthesis. So what is meant by logic synthesis? Logic synthesis generally will give you what? This front-end simulation. I was talking about logic simulation. Next one is logic synthesis. Basically, logic synthesis give you, it extracts gate level circuit. It extracts gate level circuit. So for which you have written your program. It extracts gate level circuit. Next one is what? It creates netlist. You know, netlist is a common word used everywhere. So netlist is something but it defines the logic cells and their interconnections. So it's a program way of writing it, right? So that is something called netlist. So we have two schematics when it comes to logic synthesis. That's what I just wanted to focus. One is RTL schematic, the other one is technology schematic, isn't it? What is RTL schematic? RTL schematic is nothing but register transfer schematic. So it will give you gate level circuit. Generally, it will give you gate level circuit. So my focus today, first start of the presentation, I'm going to focus on this technology schematic. So what is exactly technology schematic? What is exactly technology schematic? Yeah, it consists of LUDs. The thing is, technology schematic is based on the FPGA which you are going to implement. Based on the FPGA which you are going to implement. See, you have plenty of FPGAs, starting from ATAL FPGA, Altera, Xilinx. But most commonly used in our labs, we used to have Xilinx, Spartan FPGAs we use, right? But why? What is the use of this technology? And you are going to dump the program into FPGA. The basic problem of FPGA is FPGA do not understand your digital circuits. If I'm defining AND gate or OR gate in my program, the FPGA will not understand. Every FPGA is having its own architecture. Every FPGA is having its own architecture. Basically, the FPGA is a subset of the programmable logic units. We all might have heard about this PLD, right? PLD market. What is PLD? PLD is nothing but programmable logic devices. So, programmable logic device, basically, there are three classifications of programmable logic devices. One is PROM, PLA, and PAD. Programmable internal memory, programmable array logic, and logic. Whatever the FPGA, CPLDs, complex programmable logic devices, these are all the subsets of programmable devices. These are all the subsets of programmable devices. But if you just look at, see, I'm going to talk about not only Xilinx, I'm going to talk about few other basic fundamental FPGAs today. So this already you might have seen because you have a Xilinx FPGA in your lab. I think Spartan you might be using it. Ping board is there. Okay, so you will be, I mean, like, because Xilinx, why it is realized using LUT? LUT is nothing but it's a lookup table, right? Lookup table is nothing but just the output of the circuit. Just the output of the circuit will be realized. If you take an AND gate, for example, the output will be 1. If one of the input is 0, your output will always be 0, otherwise 1. So it means 0, 0, 0, 1 for a 2 input AND gate. That will be stored in the lookup table. So that is nothing but lookup table, which means the output of that particular circuit will be stored in the cells. That is nothing but lookup table. Okay. My focus today is I just wanted to talk about FPGA. What is FPGA? FPGA is it is a subset. As I said, it is a subset of PLD, programmable logic device. Right? It has a volatile memory. It has a volatile memory. You know, once you switches off the power, whatever it is being stored in the FPGA will be erased. So that's the one advantage we have, right? But whatever the tape out IC we have, that we call it as what? ASIC. You know that, right? ASIC. ASIC is application specific integration. That is different. That is after completing the entire design flow, whatever the IC you get from the fabrication I'm talking about, that is nothing but application specific integrated circuit. Okay. So what is the difference between ASIC and FPGA? People used to talk, but you cannot compare ASIC and FPGA always. just a different convention. But always people ask, what is the difference between ASIC and FPGA? The FPGA is reconfigurable, it is reprogrammable, and ASIC is only once you can able to program. But which is more advantageous? Which is more advantageous? Obviously, when you just look at FPGA is, when you compare with ASIC, the power consumption will be more. Because in FPGA, you have 300K complexity. For every 300K, you have a dedicated spaces in the cell. So every space will consume some amount of power, whether you are using it or not. We are using only 12 gates, but the area is already consumed. You cannot do that because it's a already general purpose IC. You cannot modify the FPGA according to your requirement. And there is no difference between ASIC and FPGA, right? So we used to take ASIC. ASIC is nothing but very crisp one. 12 gates. I will manufacture only for 12 gates. I will manufacture only for 12 gates. So which means the power consumption will be very less and the area consumption will also be very less. Right? So that's the reason ASIC is always advantageous. But why we do all this actually? What is the purpose of it? Directly I can go to the fab and I can take my, because I am writing a code. Always I am writing a HTML code and I know my design. Okay. I do simulation, okay, simulation is working fine. I will take the design and I will directly go to the fabrication. Ask that guy to manufacture an IC. That is not possible. The reason is fabricating a high complex IC is very expensive. You know that. You all might have seen, like there are several videos related to the Texas Instruments videos, how they use a clean room and manufacture an IC. It is very expensive, and at the same time, even temperature and humidity affects the manufacturing of an IC. There is a research. Recently, I read a research article. You will be surprised to it. They have a clean room, and they used to wear all the masks inside the clean room when they do this fabrication. So there are several processes they do it. It's generally an electromechanical process. Fabrications. They bring a barrel of silicon, right? They slice it, right? All the process, etching, diffusion. These are all the fabrication steps we study in VLSI. All the processes will be done in that fabrication. So what happens is when they walk around, the design engineers, when they walk around the fabrication plant with this clean room and neatly maintained shoes inside, there are still micro and nano dust particles which is going around the plant. So there is a research which is going on to evaluate the dust particles if a person walk around 2-3 times in that particular plant for 1 hour. That particular dust, micro and nano, which means you cannot able to see on your eyes. Those dust particles you cannot able to see on your eyes, right? So those dust particles will be evaluated and how to optimize the dust particles so that the performance of the manufacturing will get increased, right? That's the reason what they have decided is the so much complex factors we have in fabrication. That's the reason what they have done. So when they are doing the front end design, so they have to ensure, like when they go for a fabrication, if something goes wrong, the mistake should not be from the front end design because it is easily solvable, right? So that's the reason people do simulation, synthesis. Then FPGA is actually a prototype IC. Prototype IC means what? It is like you are dumping the program into the IC platform and checking it. It's something what I say is always it is just used for the verification purpose. In real time you won't find ICs. In all the mobile phones you have, right? So many ICs you have. In the processors of the computers you have ICs. So have you ever seen that, like these kind of things, these FPGA boards are there? No. FPGA is actually a general purpose. General purpose means in the starting level of my design, I just wanted to ensure that my design is working fine, right? So only for that particular purpose. For small projects, people used to do it. That's fine. It is even acceptable. But the reason is because we cannot afford fabrication. So I want to make an IC for my application. It is not so easy because there are very few fabrication plants in India. You know that. Only small in fabrication we have in IISc Bangalore. That is only meant for research application. Even you cannot go for any industrial application fabrication. You cannot do that. Right? The center one is a logic cell, and across this we have an interconnects and IO packs. Right? So this is actually a general purpose FPGA. This is the structure of the general purpose FPGA. So which means how many logic cells you can make it in this? 4 cross 4 it is, right? 4 logic cells, 5, 2, 3, 4, and across this horizontal vertical 4 cross 4 it is. So if you have 300K, so that many number of cells will be there. Where you can able to visualize all these dedicated spaces and cells in the tool, right? FPGA. So there are basically the FPGAs are classified into 3 types based on implementation architecture, logic implementation, and interconnect technology. So based on the implementation architecture, there are 2 classifications. One is symmetrical based architecture, the other one is row based architecture. So how symmetrical based architecture works? This is a row based one. So the one which I have shown here, right? This is a row based one. Row based one means the logic cells are placed in a row wise, right? So just look at this, the difference between symmetrical and row based. This is the way the FPGAs are classified. Got it? So this is the structure of it. This is a symmetrical one. You have an interconnect. But here, if you just look at row based, this is also an interconnect. Cells are placed in a row wise. Got it? This is the basic difference between symmetrical and row based. So now I just wanted to talk about the next classification is logic implementation. This is very, very important. So I just wanted to focus more on this logic implementation. So already you know about lookup table, right? Lookup table is related to Xilinx FPGA. Lookup table is related to Xilinx FPGA. There are fundamental other FPGAs, that is multiplexer based FPGA. Multiplexer based FPGA. So what is actually lookup table based FPGA, multiplexer based FPGA? Every FPGA is having its own architecture inside the FPGA. So whatever the function you do, whatever the function you write as a program, that will be realized in terms of that particular architecture and it will be dumped into the particular setting. See, for example, I have multiplexer based FPGA. It is made up of 3 2:1 multiplexers. The basic architecture is made up of 3 2:1 multiplexer. 3 2:1 multiplexer means how will you realize a 4:1 using 2:1? You remember, no? In the first level you have 2 2:1, in the second level you have 1 2:1. So that is the basic architecture of an ATAL-1 FPGA. That is a multiplexer based FPGA. So what they will do is, see, you have a function. See, for example, I am writing a program for a half adder. Half adder is having sum is equal to A XOR B. So for example, so what I will do, I will equate that function in terms of this multiplexer. So it will be mapped to it. So which means the system, the FPGA system will not understand whether it is a AND gate or OR gate. The digital conventions will not understand. So the FPGA knows only its architecture. So all the functions, whatever you do, it has to be mapped to that particular architecture, right? So that is nothing but logic implementation. So I just want to talk about this. So this is FPGA based things. We have multiplexer based FPGA. There are 3 types of multiplexer based FPGA. In that ATAL-1 FPGA, ATAL-2 and ATAL-3. It is all different versions, updated versions of the FPGAs. They started with actually ATAL-1, which is only meant for the combination circuits. So you cannot realize sequential circuit. You can realize sequential circuit, but it will be treated as a combination circuit. It will be treated as a combination circuit, which means like the memory element will not be considered. The memory element, the previous values you cannot consider it. It will be treated as a normal expression. So you have ATAL-2 and ATAL-3. We have both combinational modules and sequential modules separately for ATAL-2 and ATAL. Right? So this I just want to talk about. So this is a basic architecture of ATAL-1 FPGA. This I showed you. This is 3 2:1 multiplexer. 3 2:1 multiplexer, which is generally made up of 4:1 using 2:1. 4:1 using 2:1. So only difference we have here is in the selection line what you have. You have an OR gate. Got it, no?